Right, today's lesson is on something called margin of error, which is something you've probably heard of before. But before we get to that, why don't you read through this warm-up, going back to those types of studies again. It says, how could the following observational study be converted into a controlled experiment? Jennifer goes to a basketball clinic every Tuesday. She is watching fifth grade athletes with the goal of determining if the amount of time they spend practice shooting before the clinic has an impact on the number of shots they make in the game at the end of the clinic. I remember this is an observational study right now because what's not being imposed on these people? A treatment. So at this point, all she's doing is observing and making notes. So since it's just an observational study, she can't determine any cause and effect relationship. If she wanted to do that, she'd have to turn it into an experiment where she'd have to put some sort of treatment. So why don't you think for a second on how she could make this into a controlled experiment, and then I'll give you what I said. All right, did you come up with anything? Okay, well, here's what I did. Anytime you see controlled experiment, I think, okay, that means there's probably got to be two groups. So make two groups. And how you make the groups is important in an experiment. So if they ever ask this on a test or something, you need to say, make two groups by randomly assigning um, 10 fifth graders to one group who must practice for, I don't know, let's just make it up. They spend time practice shooting, so who must practice for 20 minutes before the game. And the other group who must not practice. So, and 10 students to another group who does no practice. Compare the number of shots each group makes in the game. Okay, so that's the general idea. But again, you've got to say something about randomly assigning. Because if you don't say that, then you could be assigning the 10 best players to the group who's practicing and the 10 worst players to the group that's not practicing. So it'd be lurking variables. By randomizing, it gets rid of some of those lurking variables. And then by giving one group a treatment, in this case, the treatment is practice for 20 minutes, you can see if there's any effect in the number of shots that are made in the game. Okay, there's definitely other answers, and if you want to check if yours is right, feel free to email me and ask, but that's the general idea. Okay, so today we're talking about margin of error. And here's a headline that was in a newspaper a few years back. 89% of high school students want air conditioning. But then you got to read the fine print. The fine print says the poll conducted in June of 2015 at randomly selected New York public high schools. Sample size is 2,500 and the margin of error is plus or minus 1.2%. Now, first of all, what do you think about this study? You got to evaluate it and say, is that a good study? Well, there's some potential lurking variables. First, when was the poll conducted? In June 2015. What's the weather like in schools in June usually? Pretty hot, right? So if you're polling these people on the hottest day of the year, they probably want air conditioning. If you're polling them in the middle of winter, maybe you wouldn't get 89% say they want air conditioning. So timing is definitely a lurking variable. Now, the other thing we want to talk about is this, plus or minus 1.2%. what is this? That's what we're going to look at today. If you've ever seen statistical studies in the news, you usually see something about plus or minus some percentage. So that means this could be as high as 90.2% and as low as 87.8%, which is a pretty small difference. But what we've been seeing the last few days, we know that sampling distributions are a method that statisticians use to estimate true population characteristics without surveying the entire population. Okay, so the entire population of New York high schoolers weren't asked this question. It was a small random sample, 2,500. 2,500 is relatively small if you think about all the high schoolers in New York State. But they're claiming that 89% of high school students want air conditioning. They're claiming something about the entire population characteristic here based off of their sample. And they probably used a sampling distribution to do it. It says, but how confident are we that our results reflect the true entire population? That's where this thing called margin of error can help us. So margin of error is a measurement of how accurate our sample is relative to our population. And it gives us a range of plausible values for our population characteristic based on the sample statistics. So based on the samples that I've got and the stats that I calculated from those samples, it gives me a plausible value for what the true population characteristic would be, whether it's the true proportion of high schoolers that want air conditioning or something else. I want to show you a couple other pictures I took straight off of a news article. And these are both kind of old. Here's from the CBS News 2016 presidential nomination tracker. This is before the Iowa caucus happened. So this is when it was between Hillary Clinton, Bernie Sanders, and someone named O'Malley. Not very political. But anyways, for people who look at this, they're saying, oh, well, Clinton's in the lead. She's winning. True, based on this sample. But look down here. MOE plus or minus 8.6%. That's a huge margin of error. If these could all be fluctuating by 8.6%, let's say Bernie Sanders got 8.6 more and Clinton got 8.6 less, what would happen? Well, all of a sudden Sanders would be winning. So margin of error, you want to keep this small to keep your results not fluctuating. By showing this in small print down here, they're basically saying they have no idea who's in the lead. It could be Clinton, it could be Sanders, but it could just as well be, probably not O'Malley, because you're not going to go up or down 8.6%. But between Clinton and Sanders, they could flip-flop because of that huge margin of error. So your results are only accurate within that range of plausible values. Here's another one. I'm not even sure what this was asking, but Elon University in North Carolina asked if the public option becomes available, public option for what, I don't know, would you use it? 41% said yes, 43% said no, 15% don't know. So would you not make the public option available because more people said no than yes? Well, you shouldn't, because down here, they're showing you plus or minus 3.8%. That's a lot smaller margin of error, which is good. But again, if you add 3.8% to here and subtract 3.8% for here, all of a sudden there's more yeses than nos. So that means it's a toss-up. They're not really saying one way or the other. Okay, so margin of error is important to consider when you're looking at statistical studies. So how can we accurately estimate margin of error? The way we're going to do it, and there's different ways, but the way we're going to do it is using standard deviation, how spread out the data is. And this is, in the last video or last lesson, you might have seen me say that there was a certain percentage number that's important. 95%. 95% of data normally falls within how many standard deviations of the mean, assuming a normal distribution. That was plus or minus 2 standard deviations from the mean. And that's what our margin of error is. So our margin of error, we're always going to calculate it by doing plus or minus 2 standard deviations of the sampling distribution. Now, I write of sampling distribution because I'm going to refer back to this a lot. That standard deviation, I'm not talking about the standard deviation of a single sample. I'm talking about the standard deviation of the distribution of all the dots. So how spread out all the dots are. And we want to talk about how can we make this as small as possible. Okay, so what I'm saying right here is if your sampling distribution is normally distributed, which they generally are if you take enough samples, here's the true population mean or the true population proportion, whatever you're looking at. If you look to -2 standard deviations of the sampling distribution to +2 standard deviations, you're going to get 95% of the data. So we can say we are 95% confident. This is a phrase you're going to see, that the true value falls within this range. All right, it'd be pretty unlikely that one of these dots over here was the true population proportion. But we're 95% confident that the true proportion or the true mean is somewhere in between here. Okay, now remember, there are ways to make this standard deviation number smaller, which would in turn make the margin of error smaller. And we'll talk about those as we go through this lesson. Okay, so interpreting the margin of error. Whether I have a mean or whether I have a proportion, depending on what I'm studying, plus or minus the margin of error. When you see plus or minus the margin of error, again, think of that as 2 standard deviations. If I take that mean and add or subtract 2 standard deviations from it, the interval created gives you a range of plausible values. For true population characteristic. Range of plausible values is another phrase you're going to kind of keep seeing a lot. All right, let's see some examples. Schools decided that the pacer in PE class was getting too boring for students. I really wanted to try the pacer, but that's a side story. Schools want to do a timed mile for 11th graders instead. So this is one random sample of 10 11th graders, and we're going to ask you to run a mile mid-year and get their times in minutes. Find the sample mean using your graphing calculator. Okay, so I could just add these all up and divide by 10, but let's throw these into L1. If I go to stat edit and put all these numbers in, I'm going to clear out what I have. So I've got 6.5, 8.4, 8.1, 6.8, 8.4, 7.7, 9.1, 7.1, 9.4, and 7.5. Okay. If I want the mean, we're going to do that one variable stats thing that we saw on the first day of statistics that you should have known from Algebra 1. Remember, that's, if I want to get to that, I go to stat, calc, one variable stats. And I shouldn't have anything in frequency list because it's just one list of numbers. And the first value we wanted, 7.9. So the mean of this one sample is 7.9 minutes. Okay. The school then collected 50 random samples of 10 students and calculated the sample means. The standard deviation of their sampling distribution of 50 sample means was 0.6 minutes. Based on the standard deviation of the sampling distribution, what is the margin of error for the sample mean estimate? All right, this is where people start getting confused. Let's think about what I'm talking about here. I'm making a sampling distribution. So this one sample was 7.9. So if I wanted to count this one sample, I could put a dot right here. That's 7.9. But then I'm saying I'm collecting 50 samples of 10 students. So here's one sample. I'm doing this 49 more times. And I'm calculating the mean every time. So let's say the next time I get it, they're a little bit faster, and they're 7.8. That's the mean. So I put a dot at 7.8. Maybe the next time, they're 7.9 again. So I put another dot there. And then the next time, it's at 8.0. They're a little bit slower. So I put a dot there. And they're saying I'm doing this 50 times. So eventually there'll be a bunch of dots, different places. You get the idea, right? I'm making a sampling distribution. They're saying the standard deviation of the sampling distribution. That's important. Is 0.6. So this is the standard deviation of all of the x bars, of all the means. So all the dots. It's not the standard deviation of one sample. It's the standard deviation of the whole distribution. That's how I calculate the margin of error. I use margin of error, and I say that that's just equal to plus or minus 2 standard deviations of the dots. So here I can just do plus or minus 2 times 0.6, which would be 1.2. So the margin of error is plus or minus 1.2 minutes. Okay, so now it says suppose the mean of the sampling distribution of sample means was 7.9. So the average of all the dots comes out to be 7.9. So again, I'm not talking about the mean of the one sample, which happens to be that as well. I'm saying if I average all of my dots in the whole distribution, let's say that comes out to be 7.9. Using the margin of error, find the range of plausible values. Okay, so whenever it says find the range of plausible values, that means we're going to do mean plus or minus the margin of error. So the mean of the sampling distribution was 7.9. We're going to add and subtract the margin of error, which just came up to be 1.2. So I'm going to add 1.2 and subtract 1.2. If I subtract 1.2, I get 6.7. If I add 1.2, I get, what, 9.1? So what this means is that the middle 95% of data falls between 6.7 minutes and 9.1 minutes. So what does that mean? Interpret it in the terms of this problem. So we did these this sampling distribution to figure out what the true average time for all 11th graders at this high school was. And even though the sampling distribution told us that was 7.9, that's within a margin of error. So what this would tell us is the plausible values of the mean mile time of all students, or I should say of all 11th graders at this high school is between 6.7 and 9.1 minutes. Now, that means that the average mile for the true population is somewhere between 6.7 to 9.1. That's kind of a big range, and you might guess that even without doing this study. So that's what I was saying. You might want to think of ways that you could make this a smaller range, kind of narrow down where that mean would be. And the only way to do that would be to make your margin of error smaller. And the only way your margin of error is going to be smaller is if your standard deviation is smaller. And remember, standard deviation we saw in yesterday's video is calculated in part based on the sample size. So my sample size was pretty small, 10 students each. If I wanted to reduce this standard deviation, I could increase the sample size. If I make bigger sample sizes, my values are going to be less spread out, which means my standard deviation is going to be smaller. So if you want to decrease margin of error, you want to increase sample size. Think about that. I'll mention that again. All right, last part. Is the value of 6.8 minutes plausible? Why or why not? Well, it's plausible if it's within the range of plausible values. So, yup. 6.8 is within the range of plausible values. So the true average mile time could be 6.8 is basically what that's saying. Okay. Let's go to the next page. What if we're only given one sample instead of the whole sampling distribution? What if you just take one sample and you want to try to come up with a margin of error? Well, again, margin of error is still plus or minus 2 standard deviations. And what I mean by that is plus or minus 2 standard deviations of all the sample means. But using the formula that I showed you yesterday, that's the same as saying plus or minus 2 times the standard deviation of a single sample over the square root of sample size. That's how this was calculated. Okay? So, suppose students can rate their math class from 1 to 10, 10 being outstanding. Random sample of 10 FHS students produced the following ratings. I don't know who these people are saying their math classes have a rating of 1, but they're clearly misguided. Calculate the sample mean based on these ratings. Okay, so I need to go to my one variable stats again. So stat edit, I can clear out all these mile times and put these in instead. We've got 10, 5, 2, 4, 1, 4, 8, 10, oops, just clicked off. Okay, 10, 5, 2, where'd all these numbers go? Okay, 4. Hang on a second. All right, sorry, I think my calculator froze there. Let's try this again. We're going to put in 10, and then 5, 2, 4, 1, 4, 8, 10, 1, and 6. Okay, so I want the sample mean based off of these 10 samples. So again, I could add these all up, divide by 10, or I could use one variable stats and look for x bar. And that's what I'm going to do. So stat, calc, one variable stats, and the mean comes out to be 5.1. Okay. Calculate the standard deviation to 3 decimal places. So that's also in one variable stats. It's right here. Standard deviation is 3.208. Okay. Use part of the formula above to calculate the approximate standard deviation of the sample distribution of sample means of size 10, on the nearest thousandth. Okay, so now this is saying use part of the formula, means they want you to calculate the standard deviation of the sampling distribution. So that was this formula that I showed you yesterday. And again, you don't have to worry about memorizing this one. This one's always going to be given to you. It's standard deviation of the sample over radical n. So 3.208 over radical, what's n? 10, because the sample sizes are size 10. So if I do that, I get 3.208 divided by radical 10, 1.104, or 0.14. Okay, so that's the sampling distribution's standard deviation. That's what I need to use to find margin of error, not a single sample, the entire dot plot. So now find the margin of error based on this sample, and then find the range of plausible values for the true population mean. Write a sentence interpreting the value of the margin of error and the range in the context of this problem. Okay, so margin of error, first off, is equal to plus or minus 2 standard deviations of sampling distribution. to make sure you're using the correct standard deviation. It's 2 times 1.014, which comes out to be plus or minus 2.028. So that's the margin of error, first off. And then if I want to find the range of plausible values, I take the mean and I add or subtract 2 standard deviations. Or in other words, I'm taking the mean plus or minus the margin of error. Now, the only mean I have to go off of is my sample mean. So we'll hopefully assume that that's going to be representative of the whole population, plus or minus 2.028. And this will give me a range of plausible values. If I do 5.1 minus 2.028, I get that number. And if I do 5.1 plus 2.028, I get that number. So that means the true rating, average rating of all students in this high school of their math classes is between 3.072 and 7.128. Okay, so that's exactly what I'm going to write to interpret it. The plausible interval for true rating of all FHS students is between 3.072 and 7.128. And again, that's a fairly big range. That means that average could be a 3, which is a pretty low rating, to a 7, which is a pretty high rating. How could you make this range shrink? How could you make it smaller? By making a larger sample size. The sample size was only of size 10. If I made it a bigger sample size, this number would be smaller because I'd be dividing by a bigger number, and the margin of error would be smaller. Okay, would you say a rating of 8 is plausible for the average? No, it's outside that range. No, not in range of plausible ratings. So we're basically looking, is it inside the range or is it outside the range? And what that means is it's unlikely that the true rating or the true average rating of all the high school students here is 8. Now again, statistics is annoying. It's not saying it's not 8, it's saying it's unlikely it's 8. It's not in that 95% range, so it probably isn't. When they ask the question, is it plausible, you basically just have to figure out this range of plausible values by taking the mean plus or minus 2 standard deviations. And if the value that they're asking is within the range, then is it plausible? The answer is yes. And is the value outside the range? Then the answer is no. And when I say range, I mean plus or minus 2 standard deviations. Mean plus or minus 2 standard deviations. All right, so we've been talking about sample means. Let's do a couple examples with sample proportions, and then we'll be done. So margin of error for sample proportions, same idea. The margin of error is going to equal plus or minus 2 standard deviations. But when I say 2 standard deviations, I mean plus or minus 2 standard deviations of all the p-hats. So it's still of the sampling distribution. And if I substitute that formula that I showed you yesterday, that means plus or minus 2 times radical p times 1 minus p over n. Because this formula here is what I showed you yesterday, was a way to calculate the standard deviation of all the p-hats, of all the dots. Okay, a polling agency collected 100 random samples of 50 US adults about their favorite soda. What's 100? 100 is the number of dots. Of 50 US adults, what's 50? That's the sample size. It was found that the average of all the p-hats was 0.31, so they favor Coke, with a standard deviation of the sampling distribution of 100 sample proportions of 0.07. So again, this is a standard deviation not of a single sample, but of the sampling distribution. That's what we need to find margin of error. So based on the standard deviation, what is the margin of error for their sample proportion? I do not need to use this formula because the standard deviation they're giving me is the standard deviation of the distribution. That's what you've got to watch out for in the homework. Are they giving me the standard deviation of all the p-hats, or are they giving me the standard deviation of one sample? If it's of all the p-hats, you can just plug it right in to the formula. But if it's just of one sample, then you've got to find the standard deviation first and then plug it in. So this one's easy because I can just do margin of error equals plus or minus 2 standard deviations of all the p-hats, which is plus or minus 2 times 0.07, so plus or minus 0.14. What is the plausible range of values for this study? Plausible range, we take the mean, plus or minus 2 standard deviations. Well, in this case, the mean is represented by this symbol. So it's the mean of all the p-hats plus or minus 2 standard deviations of the p-hats. So it's going to be 0.31 plus or minus. Now this is what I just found up here. So 0.1 or 1.4. Or sorry, did I say that wrong? It's not 1.4, it's 0.14. Sorry. Okay. So if I subtract 0.14 and add 0.14, 0.31 minus 0.14 would be 0.17, and 0.31 plus 0.14 would be 0.45. Okay, so interpreting that, we could say we are 95% confident that the true proportion of US adults who favor Coke is between 0.17, so 17% of adults, and 0.45, 45% of adults. Again, it's kind of a big range. If you say 17% of the population prefers something versus 45%, that's a big disparity here. How could I make this smaller? With a larger sample size. So let me say that again. Note a larger sample size would decrease the margin of error. Because as soon as you have a large sample size, your dots are less spread out, standard deviation is less spread out. Is 0.41 a plausible proportion who would prefer Coke? Yup, because it's within the range. Okay, last one. In a sample survey, 50 people were randomly asked about their favorite soda. 38% of them listed Coke as their favorite. One sample, not a distribution. Based on the sample proportion of p equals 0.38, what's the standard deviation of the sample proportions of this size? So if I were to create a sampling distribution, what would the standard deviation be? Standard deviation of all the p-hats. That's where I have to use this formula. Because again, this is one sample, whereas in the last example, it was a whole sampling distribution. So if I have just one sample, I need to find the standard deviation of sampling distribution. I use this formula, which again, you don't have to memorize, it'll be given to you. So we're going to use 0.38 times 1 minus 0.38 all over what's n? Sample size, 50 people. So let's see what that comes out to be. Square root of, I'm going to use alpha y equals 0.38 times 1 minus 0.38 divided by 50. And it comes out to be 0.0686-ish. And finally, what's the margin of error for this survey? What would be an acceptable range of values for the population proportion? So margin of error, it's plus or minus 2 standard deviations of the sampling distribution. So that number I just calculated. So plus or minus 2 times 0.086 or 686. So that times 2 means plus or minus 0.137. 0.1372, I think it was. Didn't tell us what to round to. So the acceptable range of values would be from that sample proportion of 0.38, add or subtract the margin of error, 0.1372, and that will give me my range of plausible values. So 0.38 minus 0.1372 gives me that number, and 0.38 plus 0.1372 will give me that number. So an acceptable range would be between about 24% and 52%. So we'd say about between 24% and 52% prefer Coke. All right, so big thing to remember is you want to use the standard deviation of the sampling distribution when you're calculating margin of error. Why don't you grab your homework real quick, just so I can talk through a couple things and give you some hints. Okay, so let's talk through a couple things just to give you some hints. Number one, I think you should be fine with is sampling size increases. What does that do to the margin of error? This one, they want you to find the margin of error using this formula. So they basically give you the formula and just plug in the pieces. This is where it gets confusing. And these questions are easier than you think. A sampling distribution of sample means is created by taking 40 random samples, each of size 100, and calculating the mean thumb length. So what's 40? 40 is number of dots, because it's a distribution. What's 100? That's your sample size. The mean of the distribution is 1.8 inches, so that's the mean of all the dots. And the standard deviation of the sampling distribution is 0.2 inches. Standard deviation of all the dots. So if I want the margin of error, that's just plus or minus 2 standard deviations of all the dots. And that's exactly what they gave me right here. So this should be pretty easy to calculate. Range of plausible values, that's the mean plus or minus the margin of error. And then tell me if that's within it or without it. Number 4, data was collected regarding the proportion of U.S. adults that sing in the shower regularly. A sampling distribution of sample proportions with sample size 50 yields a mean proportion of 0.67 and a standard deviation of 0.08 for the sampling distribution. Again, they didn't really tell you how many dots this time, but each of the sample sizes, so that's n, was 50. But it doesn't really matter how many dots there are because this is the mean proportion of the sampling distribution. So this is the mean of all the p-hats. And this standard deviation of 0.08 is the standard deviation of all the p-hats. So it's already the standard deviation of the sampling distribution. So again, part A, when I want to find the margin of error, I'm just doing plus or minus 2 standard deviations of all the p-hats, which they gave me. So that should be easy. Tell me the plausible range of values with an interpretation, so mean plus or minus the margin of error, and then tell me if Lady Gaga's claim is plausible. Okay, last one. In a survey of 125 students, 64% of them preferred to start the school day an hour later. This is one sample. This is not a distribution. So one sample, not distribution. So calculate the margin of error using this formula. We need to figure out what the standard deviation is, and that's why they give you this formula. So if you just plug these numbers in where they should go into this formula, you'll get the margin of error. And then I want to know if 70% is within the range of the margin of error. Okay, so don't overthink this homework. Most of the information is given to you, but give it a shot and check your answers. And as always, send me an email if you got questions. Good luck.